Okay, ELE 155. We're still talking about magnetic induction, or inductance is the name of the electrical quantity we assign to things that manifest this effect. And so I have a circuit here, and I'm zoomed in on it right now, but you will see in this circuit there is an inductor here. It says 1 capital mH. That should be 1 lowercase mH, 1 millihenry. And although the colors aren't coming out right, this is a 1 k ohm resistor. So given that that's the case, I'm going to zoom out to a schematic I have here. So I'm going to come out, and I may have to refocus. We'll see how it goes. So here is my schematic, and what I have, you'll see in a second, I have a square wave generator, and it has a positive side and a negative side. And this square wave generator, I'll make another note here. This square wave generator produces an output. It goes from 0 volts up to 1 volt, okay? Like that. And it's square, so it's high about half the time. So that's the waveform that I'm driving into the circuit. And this artistic rendering here is an oscilloscope probe. It's going to measure the voltage at this point with respect to time. And this particular this guy repeats this cycle. This guy is 50, and I'm using my pencil now, it's been hard to see, but 50 kilohertz. That means there's 50,000, that's the K, 50,000 of these where you go up for half the time and down for half the time. 50,000 of those cycles every second, okay? And if there's 50,000 of those every second, all right, then each of those has a period of 20 microseconds, okay? Meaning the time from here to here is 20 microseconds. Well, be that as it may, let's take a look at more of the circuit if we can. I'm going to shift things up here. And by the way, these two scope probes, this scope probe right here, it's a little hard to see. Maybe I can bend this back. Now, this scope probe, if you see the gray, it's actually attached to this red lead which comes from the generator. And that is this guy right here, and that's channel 1 on the oscilloscope, the yellow trace. This guy here is connected right where the inductor and resistor meet, and that's channel 2 on the oscilloscope, which has a green trace. Now, let's see if we can get this all. So there's our circuit, and maybe I can keep our circuit there, and then kind of go in on this thing. You can sort of make out the colors here. The yellow, if I turn off the green for a second, let's see. You can see the yellow is pretty much a square wave. There's a little compensation I need to do in order to make that truly square, but I think the generator is straining a little bit, and so I got just a hair of overshoot. But if you count this as 200 millivolts, that's 1/5 of a volt. So I start down here at ground. There's a little ground symbol right there, kind of hard to see. But ground, so that's 1, 2, 3, 4, 5. 5/5. That's 1 volt up there. You can see we're not quite making it all the way to 1 volt. But that's the precision that we need doesn't have to go there. Also, you can see over here it says frequency 50 kilohertz, and it's continually measuring it, and sometimes it says 49.999 or whatever. The peak-to-peak voltage, as we say, from here to there is 1 volt. It says 1.03 volts. And then this little notation up here, it happens to say 5.000 microseconds. So each of these divisions is 5 microseconds. And I might be able to let's see. Just bringing the grid, so you can see the grid a little bit better. So height-wise, it's 1, 2, 3, 4, almost 5, and so this is 5 times 1/5 of a volt, 200 millivolts per division on the yellow. So this is our square wave, or close to it. All right, and that's being measured. By the way, this is the generator output here, and so I'm just going to go back. I set up this generator for 1 volt peak to peak and 50 kilohertz, and I actually gave it an offset so it will go from 0 to 1 volt, instead of, say, -0.5 to +0.5 volt. So there's a square wave, and things over here happened earlier. I'm sorry. Yes. I'm sorry. Yeah. So we had this rise, and then we went along like this, and it fell. Okay, so these things happened earlier, and these things happened more recently or later. Okay, so earlier in the left direction, later in the right direction. So now let's see what happens when we add our second channel. When you add the second channel, you see that we don't have quite the squareness here. Our green channel is climbing up, and I may even change this frequency. Maybe I can make this look a little better for us. Whoa. Didn't mean to go that fast. And now, there we go. So you can see our relatively square yellow wave, and then you can see this green wave. This little hitch in the giddy up here is something in my setup, or the fact that I don't have my probes calibrated or something like that. So just ignore that little hitch thing. What we care about is the fact that, you know, as we drive this thing with a square wave, this point right here in the circuit doesn't see the square wave. There's something going on with this inductor. The current going through, this is a series circuit, so this current that's going through here is not keeping up with the voltage that's applied to the entire circuit. The square wave, you know, if this were a resistor and that were a resistor, we'd see a square wave output, and it might be diminished because of the voltage divider effect, but the waveform wouldn't change because, as I've said a million times, resistors change electrical energy into heat energy immediately, and so they don't distort any waveforms. But this this inductor here, this coil of wire that's inside that blue thing that you saw, so bring up this guy right here, that thing is distorting the waveform. And what's happening is a behavior called Lenz's law, L-E-N-Z. Is I try to change the current in the inductor. Lenz's law says whenever you try to change the current in an inductor, you will wind up changing the magnetic field in that inductor. And as that magnetic field expands to more magnetism or decreases to less magnetism, that increasing or decreasing field falls upon the very coil that's making that electric field. And so what happens is this coil becomes a generator. And it generates what they call a back EMF, a back voltage, if you will. So as I try to magnetize that, here I am right here, when I increase the current, suddenly I try to magnetize that coil. Well, as the magnetic field expands in that coil, the changing magnetic field washing across the wires of the coil. Remember, if I have changing magnetic field near wires or moving wires near a magnetic field, I'm going to generate electricity. Well, that's what happens. I'm trying to, rapidly increase the current in the inductor. Let me point to the inductor here. Where am I? There we are. In this inductor, but the inductor becomes its own generator as its magnetic field changes. The magnetic field is expanding on that inductor, and it generates a back voltage and says, oh no, you're not going to increase that current immediately. You've got to build up this magnetic field first, and in building up the magnetic field, I'm going to fight you. Okay, that's Lenz's law. I'm going to fight you on changing the current through any inductor. So the inductor itself generates its own back voltage whenever you try to change the current. So here we go. The yellow is an attempt to immediately change the current in this circuit. The inductor says, "Nice try. I'll get there, but it's going to have to be on my own time." So the inductor charges up. The current builds up in the inductor like this. Now, I'm measuring the voltage across the resistor, but the current will have the same waveform as the voltage on a resistor, because in a resistor, everything happens immediately. There's no distortion in the resistor. So I can get an idea of what the current waveform looks like in this circuit by looking at the voltage across the resistor. Let me say that again. When I have a resistor in the circuit, and this resistor is tied to ground, so I can put my scope probe right here, as you can imagine, whatever current flows in this resistor, the voltage from Ohm's law is equal to the current times the resistance. Well, the resistance doesn't change, so if the current changes, the voltage will change with the current. It's direct proportion, V equals IR. So this green waveform up here is a voltage waveform, but it's giving us an indication of what the current waveform is like. And we can take this voltage at any point, divide it by 1 k ohm, and we'll get the current. So as I change the voltage to this circuit immediately, the current won't respond immediately. And the voltage I see across the resistor, which again is an indication of the one current that flows in this series circuit, changes slowly because of Lenz's law. And I catch up here. Then I go ahead and I say, nope, no current, and I drop down. And what happens? The voltage across the resistor, there's no voltage on the circuit right now. I drop down to 0 here. Okay? But the inductor has a magnetic field built up in it, and that magnetic field is going to collapse, generating a back EMF in the inductor that fights you. So the inductor current won't drop immediately to 0. The inductor current will come down as the magnetism dissipates from that coil and gets near zero, and then we turn it on again and it does the same thing, and off again, and that sort of thing. So what you're seeing during these curved sections here is you're seeing Lenz's law, which says whenever I try to change the current in an inductor, I will actually wind up generating a voltage that fights me in doing that, and I won't be able to just snap the current change in the inductor. I'll have to work with the inductance and the magnetic field that has to be built up or dissipated in that inductor. So this, I suspect, is your first foray into seeing a dynamic circuit where there's distortion of the waveform. Remember, we could have a fancy all resistive circuit out here, and whatever waveform we put in, we would see that same waveform as a voltage anywhere in the circuit or a current. It would be scaled to whatever Ohm's law and Kirchhoff's voltage law and Kirchhoff's current law say it should be, but nothing will be delayed. Here you can see from this rising edge to here, there's a delay in what's going on. I can't expect to see a maximum voltage out here right away because this inductor is going to have to build up its magnetic field, and in doing so, as that magnetic field expands, it washes across that inductor, creates a back EMF, and fights me. So that's Lenz's law. That's distortion of the applied waveform, which we know that's going to happen, and not all distortion is bad if it's the one you intended. And it goes to a very simple rule, and that is to say that current lags behind in an inductive circuit. Notice here, the voltage snaps immediately, okay? See how the voltage goes right up? The current lags behind because things to the left are earlier. The voltage snapped right up. But the current, it took later until it built up to what the voltage was. Now we can talk about we can talk about the timing here. Let's see. So it takes, again, forget about this little hitch here. That's something in the output driver of the generator, I believe. So this guy's building up here, and he finally gets up here after about 1, 2, 3, 4, 5 of these divisions. Each division is 1 microsecond. And if we did some mathematics, if we took 1 millihenry, that's 1,000th of a henry, and we divided it by 1,000 ohms, we would get 1 microsecond. And so in 1 microsecond, we will get up to, you see there's 5 of these things, we get up to 3 of them, so about 0.6 of the voltage, all right? It's actually like 0.618 or something. So we get up to about 0.618 of the voltage in one of these time constants. The L over R is our time constant. And so we get up to, I don't know, 60, I think it's 60, maybe it's 63%. I think it's 63%, sorry. It's basically, has to do with this exponential rise here. So it's 1 minus 1 over E if you're into what the E number is. So if E is 2.718, then call it 3. 1 over 3 is 0.333, and 1 minus 0.333 is 0.666. So it's a little, it's in that area, all right? Now, here's one time constant. 1 microsecond is a division on here. So I go from here, the current starts building up. makes it up into the 61 or 63% area, whatever that is. Then in the next time constant, it actually makes it up, of the remaining amount, it makes it up another 63%, and then another 63%, another 63%. And most people say after 5 time constants, you're there. But as you can imagine, you're mathematically never there. You're always getting, 63% of the way there. Sort of a Dionysius paradox type of thing. And the same thing happens on discharge. If you come down from here, you drop down about 1, 2, 3 of these guys in one time constant. Okay? So there's the idea of time constant. Mathematically, it's L over R gives us the time. So again, once again, 1,000th of a Henry, 1 millihenry, divided by 1,000 ohms. A 1,000th of a 1,000th is a millionth, and so the time constant is 1 microsecond. And it's just a rule of thumb that a lot of people will say, well, you get ridiculously close in 5 time constants. Okay. Now, if I were to speed this up any more in frequency, okay. So if I sped this up any more in frequency, what you'll see is What you'll see is I don't have time to make it all the way to the top, and I don't have time to make it all the way to the bottom, and so I get a waveform that's, somewhere in between. And if I have way more than enough time, then, it's slowed down on this edge, but compared to the overall time, it's not that slowed down. So that's basically what inductance does. Is it opposes changes in current, and so you whenever you look at a circuit, if an inductor is involved, you're likely to see the current lagging behind the voltage on one of these waveforms like this. And let's see, what did I do here? I messed up the frequency pretty well. Let's go back up to, where were we? 50? I think we went to 100 afterwards because we wanted to see it be closer to 5 time constants. And there's our waveform. Okay, so that's a little bit about inductance in a circuit. And the same principles apply to inductors in motors and transformers and that sort of thing. But in terms of the electronics part of it, this is the kind of thing you would see happen in a circuit. Okay? One last thing. What happens if we put a sine wave into this thing? Okay. If we put a sine wave in here, what we notice is the yellow is the driving sine wave, and the green is the resulting current in the circuit. Again, we're watching a voltage to get an indication of the current. Notice that in this case, the green is to the right of the yellow, which means the current is happening later than the applied voltage. And that's typical of an inductive circuit. Current lags behind the voltage. So this magnetism of this inductor is delaying things. What's interesting about a sine wave is this is the one case, if I excite this circuit with a sinusoid, that is a sine wave of whatever proportions, the waveform I will get out is a sinusoid. So there's no distortion there. There is delay, however, and there is scaling in the size of it. And that varies as we vary the frequency. Let's keep that on sine, right? And let's go to frequency here. That's amplitude. Maybe we should try frequency. as I mess with the frequency, you can see here at a higher frequency the shift is greater and the attenuation of the sine wave is greater. As I go back to lower frequency, about 240 hertz here, they look like they're completely coincidental there. The yellow and the green are on top of each other. You can't tell them apart. What that tells me about this circuit is that it's happy letting through low frequency waveforms. In other words, I don't have any sharp changes like a square wave here. I've got a nice, slowly, smoothly changing waveform. And as long as it's slow enough, the output here follows the input nicely, okay? And I, don't seem to be losing anything. But now, if I take the frequency, let's see, way up. Let's see, what am I doing here? If I take the frequency way up, I'm beginning to lose amplitude on the output waveform, and I'm experiencing this, what we call a phase shift. Wherever you are in a sine wave, either at 0 degrees or 90, 180, 270, 360, which is the same as 0, 90, 180, here, let me do it that way. If you look at a sine wave, I come up, when I cross the midpoint at 0 degrees, 90 degrees, 180 it goes back across 0, 270 it's at its minimum, 360 is the same as 0, and I've come around to the start again, 90 degrees, and so on. You can see in this case that the 0 pattern here, actually sorry. So that's, so if I go up, I'm getting to the point now, set my triggering and see if I can get things go better. All right, up. Hold on a second. All right. So, if you look here, I'm almost, well, let's, no, jeez, let's stay there. I'm going to go back here. And when this guy crosses the midpoint, and this guy's at 45 degrees, my frequency would be 1 over 2 pi times L over R. And I'm going to do a quick calculation here. If you want to see that. Nah, this won't show up very well. I'll just do it here. So if I do 1 divided by quantity 2 times pi times L over R, anyways, and I get 159 kilohertz. And right now I am at, I'm at 150 kilohertz, so it's pretty close. So there's 160 kilohertz, and now the 0 guy is, pretty much under the 45 degree guy. That would be 90 degrees, and this guy is like 45 degrees. So there's a formula for finding the frequency at which you would have 45 degree phase shift. And this obeys that, and that's all well and good. So hopefully it's been a good exposure to some of what happens in an inductive circuit in electronics. All right, we'll see you next time. Take it easy.